Okay, so these are mass spectrometry-based proteomics data, liquid chromatography-based MS proteomics data. 20 human beings, 10 who are healthy, 10 who have diabetes. I've already processed the data somewhat. I'll talk about that here in a second. But let's look at them first. We have 65,000 rows. There are 10 columns. Why are there only 10 columns? Okay, yeah, so I have not processed these yet. This is the format of the data that, in this case, I received from the laboratory. This is kind of not exactly raw, but it's pretty raw version of the data. In particular, I don't have an M by N. I don't have an M by N matrix of numbers yet. What I do have, let's see, is, so first column is an identifier. The first few columns, 2 columns, are identifiers for the sample. For example, P8_2 indicates this was the 8th patient, diabetic person, and each person was measured 3 times. So this is 3 technical replicates for each individual. Technical replicates run in triplicate. This first row then is basically a peak that was identified to be a peptide in this individual. This particular person, we obtained tissue sample or a biological sample from them, and the second time that we ran them through the instrument, we observed something. And this something is a peptide. It's a piece of a protein. It was given a unique identifier. The people at this particular laboratory call it a mass tag identifier. So this is kind of like a read identifier, a read count identifier from next-gen sequencing, a unique identifier. This is the number that we would assign to that peptide in this sample. So roughly speaking, if we went to all the spectra for this sample, remember that we would have many spectra for this sample because of the fact that we have this liquid chromatography column that's spreading out the material into scans or material to be scanned of more homogeneous peptides or ions. Of all the peptides that were identified for this particular person in this particular replicate, this one was seen with a peak height, roughly speaking, of 254,000. If we looked at the actual peaks in the spectrum, somewhere in this particular person's mass spectra, there's that one for scan 1, there's this one for scan 2, ... bunch of scans. So we have data that could be summarized like scan number and M over Z, and we have all those dots like we saw in the picture last time. And if we zoom in at a particular place, there are these peaks coming out towards us that represent a peptide. If we're able to locate one of these little clusters, a peptide, we can do the tandem mass spectrometry to get a better fingerprint and identify that peptide. If we blew up that spot that was circled, we could figure out the charge state, we could figure out the mass, like not mass to charge, but the actual mass. Once we know the charge state, we can figure that out. We could compare to a database to say that particular peptide is peptide X. And so that's where this number came from. Among the spectra for patient 8, replicate 2, we saw many peptides. One of them was identified by searching against a database to be that one, and the number we assigned to that one is that. Here's the mass. So after, this is called deconvolving the picture in that scatter plot. Looking at this, let me go back to the paper we saw last time real quick. So here's patient 8, replicate 3, or replicate 2, and a searching or scanning algorithm finds a pattern of points that is indicative of it being a peptide. If we can find this type of pattern for a peptide, we can figure out lots. We can figure out the charge state. We can figure out the mass for the most prevalent version of this peptide. And then looking at all the peak heights that make up this little cluster, because remember there's peak heights coming out towards you, we could boil that down to a single number. We know a number. We know the mass for this peptide. We also know the time at which it eluded from the LC column. So this particular peptide came out in a scan after 0.29 minutes or something. This is a normalized time. So everything that came out with that elution time eluded together and was scanned together. We have a unique identifier. We also know, when we did the identification of this peptide, the actual amino acid sequence. When we compared against the database of all the theoretical peptides that you would see in humans and the tandem mass spec profile you'd expect for them, this was the best match for this particular feature, patient 8_2. That's its sequence. The other issue that we talked about with proteomics is analogous to the next-gen sequencing case where we have reads, but we're not really interested in reads, we're interested in genes. So we have to align or identify the reads back to genes. Here, we're not particularly interested in the peptides themselves as much as we are proteins. We're doing proteomics because we'd like to be able to say, in diabetics, protein A is different than in healthy. So if you tell me the peptide sequence and you tell me the organism, human, we could go look through the genome and all the known proteins for humans and try to find that sequence. Which protein did that peptide come from? In many cases, especially for decently sized peptides, we can make that connection unambiguously. There's only one human protein that has that sequence of amino acids in it, maybe. That's what we hope for. Doesn't always happen that way. There can, in my experience with these types of data sets, there's often at least some ambiguity. But the decision was made that this particular peptide came from a protein, and the protein also has a unique identifier. There will be multiple observations of peptides from this protein if we were to go through this data set. If I wanted to look up the details of this data set, just like we did with like ensemble identifiers for genes and HGRC symbols, we could Google this and learn something about this protein. If we did Google it, the short description of it that we would find is this. It means nothing to me, but would mean something to the biologist. That's a description of the protein. All right, so we have 65,000 of these things. Each row is a peptide that was observed in a replicate. 3 replicates each of 20 people. All right. Let's log transform the intensities. That's a common step with omics data, like with a microarray experiment. You have fluorescence intensities, and those can be tens of thousands in the scale of thousands. tend to be right skewed because you can't have negative intensities. In the same way, you can't have a negative peak height. So I have a lower bound but not an upper bound. That's a recipe for right skewed data. Log transforming is a sensible remedy for right skewed data. Often, if you have a right skewed distribution, if you log transform it, it will look more normal. So let's log transform. And then we need to construct an M by N matrix. That's what we're used to working with. All right. So this is a typo. This should be reshape. This is a good trick to know. Reshape to what? What we would like is to take the data in this format and change it to a format where there's one row per every peptide that's in the data set. How many peptides are there? Length, unique, data, mass, tag, ID. How many unique mass tag IDs are there? It's 1,400. It's 1,400 peptides total. How many proteins are there? I'm curious. 175 proteins. Okay, let's turn this into a 1,400 by 20 matrix. One row per peptide, one column per individual. Actually, let's do a 1,400 by 30 matrix. One row per peptide, one column per replicate per individual. Then we'll have to do something with those replicates. Because, for example, 30 measurements on the same person of blood pressure is not a sample size of 30. So you wouldn't want to do a t-test that includes technical replicates and biological replicates. There's correlation between those technical replicates. We need to do something about that. What I'm going to do here is so if you think about what we need to do to turn this into a 1,400 by 30 matrix, I need to find all the unique mass tag IDs and create a row for each one. The first one is 1036. I would then need to go find for P1, or for P1 underscore 1, go find the abundance for that peptide. Go find the row that is for P1 underscore 1, mass tag ID 1036, and store that number. The problem is going to be, like if we look at 1036, how many observations of 1036 do we have? Sum mass tag ID is 1036. There's 13, but we have 20 individual, or 30 replicates. 20 individuals, not 30, 60 replicates. We have 20 humans, 10 healthy, 10 diseased, and each one was measured 3 times. So I want a number for 30 assays, 30 LCMS runs, but I only have 13. And what that speaks to is something we talked about last time to do with missing data, censored data. Here's a protein from these data. This is the diabetes data. And this protein had 6 peptides. Here's one peptide. So this might be our peptide. It's not, but it might be. And for this peptide, there were these observations in the diabetics, and there was only that observation in the controls. If we went and searched for this particular peptide, it only showed up for one of the controls. So that just means it was not identified. It might have been present in the samples for those people, but just by chance, when we scooped out the material, we didn't catch any of it. Or it was present in our sample, but it was at too low of a level for it to show up in those mass spectrum peaks. It was too noisy down there. one way or another, we didn't get a number for this for many of the controls. And what I argued last time, and I'll make this picture to reiterate it in just a second. We believe that the mechanism by which these observations went missing has more to do with a censoring thing than just a completely random mechanism. You know, if you're in a laboratory setting and you buy 20 rats and you raise 10 of them on diet 1 and 10 of them on diet 2, and lightning strikes a tree outside your lab window and the tree comes in and crashes into one of the cages and kills 5 of the rats. That's missing completely at random. It has nothing to do with their healthiness or their genetic disposition or anything. If you lose 5 of your rats because they were the sickest rats or something, that's a different issue. So we have that kind of issue here. Okay. So if you wanted to do what I just described, that is 1400 by 60 matrix, 1 row for 1036. You could code that up with brute force like for loops. It's not that hard, but it's a common enough exercise or task to take data in this format, which we could call a long format, in the sense that every single observation of this peptide gets a separate row. So it's a long data set. What I would like to do is reformat it so that every peptide has 1 row. We'll call that a wide format. We talked about that in 645. Longitudinal data, we went between long and wide formats. So the task of turning this into a 1400 by 60 matrix can be accomplished by reshaping the data. I'm not going to go through the detail here, except just to say, check these functions out if you find yourself in that situation. It's common. You have a data set of one format, you need it to be in a different format. You could spend an hour writing for loops, or use a couple of functions that, after you use them 3 times, you are comfy with them. So this is going to give us a new version of our data. I have this thing, data M, which is a data frame, 65,000 by 4. Okay, and what I have so far is just replicate name, mass tag ID, class abundance. So I created a new variable, class abundance. And then what is DD? Class DD, also a data frame. Dim is 1400 by 61. Okay, so DD1, 1 to 10, 1 to 10 is just about what we want. So after applying those 2 functions, we have a 1400 by 61 array. First row is the identifier of the peptide. So I'm not going to keep that in here because it's not actually a number we're going to do anything with except to identify the peptide. The 60 numbers I really want follow. Control observation, control sample 1, technical replicate 1. Control sample 1, replicate 2, 3, and then it goes on. And it actually ordered 10 after 1 because it did it alphanumerically. Lots of NAs. All these NAs, that means that peptide 1036 was observed for at least one of the individuals in our data set, but it was not identified in that particular assay. Okay, so I also wrote code for doing the brute force version. For loops, not that hard to write, but these functions up here do it for you. And yeah, this is nice because you don't have to rewrite this type of code every time if you have these types of data. I'm going to go ahead and run this because I think I used this down below, but it gives me the same thing. (1400 by 60). That doesn't look good. Oh, I haven't populated it yet. So I set up a 1400 by 60, and now I'm going to go through and fill in the numbers. And this takes a lot longer than those two functions we called above. And apparently this is going to take a little while because I had, on my computer, I did that once and saved it to a file because it takes a little while. But I forgot to upload this version. So we'll let that run for a moment. Once we have this 1400 by 60, eventually, you know, we want to explore the data, and we'll probably want to do inference, like differential expression analysis. Out of our 1400 peptides, can you find a subset that are different? Or even better, can we map it up to the protein level and ask about proteins? Which proteins are different between diabetes and healthy? Something we have to deal with up front, though, is all the missing values. If I come back up here and look at what came out when we applied the two reshaping functions, lots of missing values. So if I came to this peptide, for example, peptide 4, and I wanted to ask, are you different between healthy and diseased? If we popped that into like t.test, we would have a problem because of these NAs. T.test is easy to deal with NAs. There's just an option where you can say remove any NAs. We could do a t-test in this case using only the observed numbers and just ignore the NAs. So suppose we had let's just think about a peptide. For peptide X, suppose we have healthy individual 1, healthy individual 2, 10, and diseased individual 1, 2, 10. But some of these are NAs. They're missing. I have a number for some, like a peak height. Some of them I have an NA. If I wanted to do a test, let's say null hypothesis that the population mean abundance for this peptide in controls is the same as the population mean abundance for diabetics, against the alternative that that's not the case. Differential expression analysis, basically. Find the interesting peptides. We might consider a t-test, two-sample t-test. 10 numbers. Usual formula is average of the controls minus average of the diabetics divided by some standard error. But you can't compute an average if some of the entries are missing. If I used t.test, I could say t.test, here's my control data, control observations, here's my disease observations, comma, space, na.remove equal true. And what that will do is it will just, if 2 of those control observations are NAs, it will treat it as if you only have a sample size of 8. And it will completely ignore the fact that there were 2 attempted observations that didn't pan out. If it was the lightning strike in the tree coming through the lab window, there's nothing wrong with doing that. If you have missing data and the mechanism by which they're missing is completely at random, which technically means there's a whole statistical theory behind what to do with missing data. But what that technically means is the probability of your observation being missing doesn't depend on the values of any of the other observations, any of the other mice. The probability this mouse dies from a tree after a lightning strike has nothing to do with those mice, has nothing to do with the observation you would have seen for this mouse either. Completely independent, completely random. When that's the case, you can just do a complete case analysis without biasing your results. That means throw away all the missing data. In our case, because a missing observation likely was censored, we have to be more careful. So here's peptide X, and we see maybe these observations for the diabetics, and we see these observations for the controls. And maybe in reality, there were some other ones down really close to 0, a low abundance peptide in the controls. And those green dots, when we looked at the mass spectra, were below the detection limit of the instrument. So while there are green dots, if we had a precise enough instrument, we didn't catch them. A complete case analysis in this example would bias the results. If I did a t-test with all those X's and only the black O's, and I treated it as if there were only 3 attempted measurements on the controls, then the average for them, the average for these 3 observed controls would be bigger and hence biased compared to the average of all of them. If you're missing some observations, and the ones that are missing would have been your smallest observations, then ignoring them will give you bias in your estimates of So a simple 2-sample t-test with these types of data is really not appropriate. What can you do as an option? There are options. There's, like I said, a whole theory of how to deal with missing data. Unfortunately, it's a complicated topic. Even more unfortunate is that it shows up so often in practice. So many, it's really frequent for you to have missing data. If there's a really small proportion of missing data, you have 1% of your observations are missing out of 55,000 attempts or something, probably not a big deal. But in our case, this is still running, there's lots of missing data. In fact, I think it's close to like 40%. Out of all of these 1,400 by 60 attempted measurements, nearly half of them are missing. So that's that's bad. What could you do? You could try to impute the missing data. If a complete case analysis is not valid, and I'm saying that it's not because of the censoring, you will get biased results. In this case, if we took the green path, a complete case analysis, we would be decreasing our statistical power. The healthies were actually, on average, lower relative to the diseased than I would be able to detect if I only looked at the complete cases, because I am completely ignoring these extra small ones. So I could try to impute these numbers if those NAs could be some sensible way replaced with a number, like the average of other observations that are similar to them maybe. Then you can proceed with a usual data analysis without worrying about the NAs. The problem with that is, let's see, remember when we talked about feature selection and tuning a model in the classification setting, we said if you're going to do feature selection and pick from your 55,000 features a subset of 100, the assessment of accuracy needs to include that feature selection step. It's a similar idea here. If you perform imputation, you're using your data to compute something and then plugging that in for missing values. If you don't do anything to account for the fact that you already used the data sum when you did that, you'll have problems downstream, just like we will tend to overfit our data if we don't include the feature selection step in cross-validation. So missing data is a problem. Imputation is one possibility, but you have to be careful because you have to incorporate the fact that you use the data to do the imputation. So there's something called multiple imputation that some software makes easy, but some software does not to implement. That's all I'll say about missing data. Another option for dealing with data like this, where we think there is censoring, censoring would say, like for one of these green dots, suppose these 3 attempted measurements for control individuals were unsuccessful. There's NAs in my spreadsheet for these, and I think that they were censored. They're missing because they were too low. Okay, they're missing because they're too low. One thing that I could do is use some techniques that were developed for biostatistics applications. Biostatistics, common application is studying survival times. How long is somebody with stage 5 prostate cancer going to survive? So you have an experiment, a clinical trial, where you follow people who have stage 5 prostate cancer under 2 conditions maybe, and everybody comes in every 6 months and you record still alive, so they've been alive such and such months. But then one of your study participants moves away, drops out of the study, and you're left with incomplete information for him or her. You know they lived until that last visit, but beyond that, you don't know when they died. Should you throw them out? Should you say they died at the last 6 months? Or what? Survival analysis is a branch of statistics that allows you to say, for an individual like that, I don't know the exact number, but I know it's at least X. I saw them 6 months ago, so I know they lived at least that long. So you get to incorporate the partial information you have with censored data. So let me just show you a paper. Okay. This actually has these data in it. So here's the data we're playing with, diabetes. Frozen human serum samples, 10 healthy control, 10 diabetics. We fractionated to remove really high abundance proteins. That we talked about that previously. And okay. So how do you do the analysis? Here's a statistical model for doing the analysis. How do I zoom in? Okay, so just briefly, statistical model. YIJKL That's protein I, peptide J of protein I, because each protein has multiple peptides, and we have to kind of roll up to the protein level if we want a p-value for proteins. Protein I, peptide J, in comparison group K. In the diabetes data, we have 2 comparison groups. And then L is replicate. So I would have 10 replicates in the control group for all of the so many peptides of protein X. I have a separate model for every protein. I want to fit this model. This is an ANOVA model, also a regression model. We could write this as a regression model if I had dummy variables for disease status, for example, and peptide membership. It would look like beta 0 plus beta 1 peptide plus beta 2 group. And the inference, or the interest statistically, is let's go protein by protein, all 175 proteins, and let's get a p-value for are you different between control and diabetic. In terms of this model, the term that we're interested in is this one. That's the group effect. In a regression model formulation of this, there'd be a beta coefficient for diabetes. And that would be specific to protein I. So let's go to protein I, fit this model, get an estimate of the group effect, a standard error estimate, and get a p-value. That's the idea. That's not any different really from what we've already talked about this semester. That's going feature by feature and fitting a model to get a p-value for that feature. It's a little more complicated here because we have peptide to protein roll-up. In like Affymetrix microarrays and next-gen sequencing, usually you do the roll-up thing and just ignore the fact that you did it. Like instead of looking at modeling at the read level, we would usually model at the gene level in next-gen sequencing. But, okay, so we're going to fit this model, and the trick is, the survival analysis trick happens down here. We don't have to go through the detail. I just wanted to just kind of walk through this briefly and say proteomics, mass spec proteomics, lots of missing data. We think it's from censoring. So the fundamental problem is similar to what we've been doing all semester. Let's go feature by feature. My features are the proteins. That's the real features of interest. Let's go feature by feature, and let's do a test. Is this feature different? Statistically significant? Interesting. I need to fit a regression model / ANOVA model. The detail that makes it a little more challenging is the fact that there's censoring. So this picture here, if you're interested, you can look at it on your own, but this is a common kind of picture or common kind of likelihood when there's censored data. And it looks like you product over all your observations. A likelihood function is a product over all your observations of the probability distribution you think that applies to each observation. When there's censoring, we have 2 components to this likelihood. If the observation was not censored, if I have an actual peak height, then I treat this like a usual normal distribution likelihood contribution. I plug in the observed peak height, and I compute a normal density, basically. Only if this censoring indicator, which is 0 if it's an actual peak, and 1 if it was censored, only if that's 0, because this turns into 1 when that is 0. When W is 0, this piece does not contribute. When W is 1, it's a censored observation. So this turns on and that turns off, and the contribution becomes something different. And it's this that is accommodating the censoring. This is a cumulative distribution function. So basically, if you know the peak height, you can say, give me the probability density of that height, of observing that height. If you don't know the height, in our case, what we're going to say is it was less than the detection limit of the instrument. All I know is that it was less than or equal to some detection limit, which the chemists who run the instrument can tell you. So this is saying, what's the probability, roughly speaking, of seeing an actual peak of such and such? if it was observed. And this is saying if it was censored, what's the probability of seeing a peak that was less than or equal to the detection limit? It's a likelihood. Maximum likelihood is a general process for doing inference where you say that's the objective function, find the parameter estimates that maximize that, and then you did your test. We did our tests with likelihood ratio tests. We got p-values and we got q-values, and that was how we picked interesting peptides or proteins. I'll show you a picture of one of the interesting ones that we found, and then we'll quit. This is the picture from, well, this is one of the proteins that was found. So this is, if you Google this IPI code, the protein in the first panel is lumicin, a lumicin precursor or something like that. It has to do with degradation of the eyes and eyesight. So out of all the proteins that we explored, there were 175 of them, this one showed up tops. This was the most interesting one. And it was reassuring to Google it and see there's publications that tie it to diabetes. So it is sensible to have picked it up. If you look at the picture, diabetics are X's, controls are open circles, 6 different peptides. And looking peptide by peptide, you can see that there is pretty clearly a trend to where diabetics have bigger numbers than controls. This was another protein that had 19 peptides, harder to see, but the nice thing about the model is that it puts it all together in a sensible way and gives you a p-value. All right. I was going to look this weekend to see if I could find some functionality in R for pre-processing LCMS data. Somebody had asked on the discussion board for like deconvolving and stuff. I'll look and see if I can find that. Monday, though, Monday will be our last lecture. Tuesday's a redefined day, but I'm going to skip it. Unless you guys have specific things you'd like me to talk about. If you do, I'm happy to come talk more. But I'm planning on Monday to be my last lecture. So I'll wrap up mass spec stuff. I will say some things to try to tie together the whole semester, and I'll be happy to answer any specific questions. Yeah. Oh, I'm sorry. Oh, boy. Okay. Yeah. Sorry. I have averaged about 2 hours less sleep a night this week than I usually get. So never mind. We're done. Okay. If you have anything else that you'd like me to talk about or questions you'd like me to answer, let me know. And I can't talk about it on Tuesday. Otherwise, I think Monday's our last. Tuesday is the last day of the semester, I think.
Tuesday's the redefined Friday, and then Wednesday's reading day, and then final start after that. So, I believe.
Yeah, I think that's right. Yeah. So reading days are not lecture days. Today's the 29th. So May 2nd, no regular course examinations. Okay, don't tell anybody. And then that's Monday. No regular course exams. It's supposed to be like a study week, you know, for finals, but we're not having a final, so. Tuesday's the last day. It's a redefined day. So, yeah. If you want me to lecture on Tuesday, if you have something you'd like me to talk about, just shoot me an email. Otherwise, see you Monday with exams. Okay, have a good weekend.